For attending the Design Professionals ABU Online. Today's topic, we are going to talk about Seismic and how that relates to our design software and even design methodologies. My name is Chad Julius. I've been with Allen Block for, over 19 years now. So I've enjoyed this industry on the engineering side, and now I get the benefit of doing a lot of the educational components. Travel when the pandemic's not here, but also these online sessions have been fantastic. So a little bit of housekeeping. I do have everybody on a listen only mode. So if you need to get my attention, I've got another screen popped up here. Just either raise your hand or even use the question feature within GoToWebinar, grab my attention that way. And just let me know when you have questions. And please do that throughout the presentation. I will do my best to answer those in real time, the best I can, so that way it's relevant to the topic that we are currently discussing. And I like to try to make this as interactive as possible. So if you've got a question, please use that feature and go from there. So again, let me know when you're going. But today's topic, as I mentioned, we are all about seismic considerations and then how we use AB walls to do that. And we do this, try to make this interactive. And one of the first things we do is we do a lot of poll questions in this. So what that means is I'm going to launch a poll, and the question I'm posing to you guys right now is, what height do you think seismic really kicks in when you're talking about a retaining wall design? And I gave you some examples here: 6 feet, 4 feet, 12 feet, and others. So let me go ahead and launch this poll real quick. So if I launch this, you should have the ability now to just give me your answer. What do you think? What is that? 6 feet, 4 feet, 12 feet, other? Boy, it's I only have a couple of you guys on the call here, but I got 100% in, and look at this. 100% of you guys, let me share these results, thought it was 6 feet. Ironically, there is no hard, fast rule. I tend to use 6 feet or 4 feet as my general guidelines, because let's face it, if you're in a high seismic zone and you've got special requirements, maybe it's retaining a parking structure or something like that, maybe the height isn't controlling, but we do know as soon as engineering gets involved, a lot of times that will trigger your seismic requirement as well. And so 4 to 6 feet is generally used, but really there's no hard rule per se, because I hate to give the old political answer, one size does not fit all when you're talking about retaining walls. So let me go ahead and hide this, and we'll get started with the presentation here. So a couple goals that I have. First, I'm going to start with our full-scale seismic testing. To me, that was the game changer for not only Allen Block, for our industry. So we're going to talk about what came about because of the testing. So there were significant outcomes and results of this. We're going to talk about how seismic has been incorporated into the industry best practices. And then the last thing we're going to do towards the end is really kind of get you into our software and maybe understand how seismic affects the slope above and below the wall and how that impacts your design. And so again, hopefully you get some benefit out of this, but please ask some questions as we go through this. I got to start with our seismic testing. We did it over in Japan. Why Japan? Well, in 1995, the Kobe earthquake hit in January, and obviously major devastation for that country. So much that obviously they invested a lot of time and resources into seismic analysis and seismic designs. And so what they did is they spent the money and created a large shake table. This table's monstrous, and they were able to actually test building components like columns and joists and stuff like that to see what the connection kind of reacts to in a dynamic environment. And they kind of got through a lot of their testing and open it up for the rest of us to maybe take advantage of. And we were very fortunate. We were approached by Columbia University, and they were in partnership with the University of Delaware, and they posed the idea of doing research on a segmental retaining wall in a seismic activity. And we jumped at it. We really felt strongly that this was something we needed to do. We had obviously retaining walls in earthquake prone areas already, and they had gone through seismic events and functioned just fine. So we were pretty confident that we were going to get some favorable results, but nothing's for sure. In fact, when we pitched the idea to the NCMA in 2002, they weren't all that keen. And the NCMA is the National Concrete Masonry Association. they're as close to, I guess, a governing body in our industry. Like we're members of the NCMA, other block companies and production partners, and even engineers and contractors are members of the NCMA, and we form committees to try to figure out what's next or what's good for our industry. And we couldn't get them to sign off and help fund the testing, so we did it ourselves. We partnered with Husker Geosynthetics, and to this day we're very appreciative of them partnering with us, because obviously this was not a cheap test when it's all said and done, but they like us thought it would be well worth the time to kind of put your money where the mouth is and get these results. And so let's dive into this here a little bit. So this is the configuration. This is actually that large gray area. And let me activate my pointer here. This large gray area is their testing frame. That's their table. So you can see it's kind of enclosed, but that whole thing moves, it shakes, it rocks and rolls. And so you can see we built the secondary frame with inside of it, so that way we could hold up our retained soil, obviously on the three sides, and then the open face here is where we had that retaining wall. And there's a lot of things happening in this thing. So you can see we put some plastic and we try to minimize the influence of that secondary frame, but we shook this thing front to back and even a little up and down towards the end of these end of these testing. But that's the frame itself. And I'm going to kind of give you a glimpse and a peek behind the curtain even before we talk about the different configurations. But this one, and I know the video sometimes doesn't always play very well through GoToWebinar, but I think it's important for you guys to watch this. This would be like of our structure number 3. So this is a top-down view. So right now I'm looking at the top of the block going down the front of the wall this way. And you can see the string lines, they're kind of overlaid over target discs that are on the soil itself. The string lines are connected to the frame. Here's the same structure now, but from a different perspective. So this is kind of the front end view. The bars that go across there are really kind of holding deflection gauges. So they have a way we can measure the displacement or the movement of that wall. So they're not supporting the wall in any means. And this is a kind of that closer fixed view. So the camera is actually on the testing frame. And you can kind of see a little bit of movement in that wall. So this would have been like our first shaking, but then every structure we did actually went through 2 shakings events. And the second time we did it, we doubled the magnitude. So this is the same structure, test number 3, but what we call at 0.8 G. So you'll see a lot more movement. You can actually see the styrofoam on the sides here, so we can kind of give a little void barrier and minimize that influence of the frame itself. But you can see that front to back movement here, because again, this is a top-down view of what you're seeing. Notice the shadow line on the back of the block. So that's kind of showing that the soil behind is starting to consolidate and stuff now. So again, the front end perspective. So now we can see how the whole frame and stuff is shaking in relation to the wall. And so you'll see that frame move, and then the wall tries to catch up to it, just like a dynamic event. You know, your flexible systems will give and take a little bit as we go through this. And you'll see how it changes in perspective. You got different dynamics. Since Japan had, or the testing company had so much information on the Kobe earthquake, both in amplitude and magnitude, that frequency is basically the Kobe earthquake and what they have on record. Major movement on this perspective. And this is the one I really like. You can see how much movement you have in that wall. And remember, this is a 10-foot high wall. So this is a massive structure running through this thing. And so very positive tests all the way through. Even on some of the structures, we would bring in like layers of white sand just to see if we get some mixing and stuff. And I'm going to let this play just a little bit longer so you can kind of see some of the cracking and deformation and how they did some of their measurements. But really, once the testing was over, then they started just kind of taking all the individual measurements. They almost did an a dig, so that way we could kind of see if we get some mixing, what kind of loads were on the geogrid. So once the testing or the shaking was done, the real work really got started. And so you can kind of see that displacement of that string line to the target disc down below. Okay, so let's get into this a little bit. All right, so as I mentioned, we did 6 structures at the Japan National Research Institute. Each structure was just under 10 feet, so 2.8 meters with a little bit of buried block, right? So, or not embedment, we tried to put it on top of soil, so it wasn't resting right on top of that metal frame. So we tried to give it as much of a real life experience as we could. And as I mentioned, 2 tests per structure. So let's start with structure number 1. Structure number 1 was kind of what was recommended by the industry at the time. Now remember, this testing was done in 2002. So this has evolved over the last 18 years even. And at the time, the standard was about, 3 core spacing. So in our case, it's 24 inches center on center because Allen block's about 8 inches tall. And in this case, we followed kind of our DOT, MOT type of methodologies where the grid lengths were about 70%. In this case, they were 0.73%, 73% of the height. So that's where the 2.05 meters comes from. Now, if we work our way down, we used our stones, which is our 12-degree system. Yes, the system works with a near vertical or 6-degree as well, but our production partner in Japan had the AB stones. And then the soils. Now, the soils got to be a little bit better than what we originally hoped. We just used a fine-grained sand, but when we did the shear strength of that tested out to be about 37 degrees, so a little bit higher than we were hoping. But this was at least a baseline, right? Something to work with. Now, the first shaking, we went to 0.4 G. Why 0.4 G? Because at the time, our uniform building code, even up and down the Pacific Rim or the West Coast there, the acceleration coefficient that they were using was 0.4. And so that we figured that was a good way to start. And instruction number 1, we just did the horizontal shaking, so that front to back movement more than anything else. Notice very little settlement and displacement after that 0.4 G. So we were very happy. And to be honest, that's what we saw out in real life too. Like I mentioned, we had walls go through seismic events. We didn't see major deformations, major movement. Now we get into the second shaking, because like all researchers, we want to kind of stress the system a little bit. So we went to 0.8 G, because now you're getting close to that 7.2 on a Richter scale, similar to what the Jacobi earthquake was. And so again, just that horizontal movement. Notice the settlement here, 60 to 90 millimeters, over 80 millimeters of horizontal displacement. So we've got some major movement. We didn't have catastrophic failure. The blocks didn't come flying off, and that was a real belief by some of the researchers. They thought the grid would maybe slip or stretch, and the blocks would kind of displace a little bit and maybe separate a little bit, and the blocks would just kind of tumble apart, or the system would kind of tumble apart. But it didn't happen, and so we did get that settlement displacement, but everything kind of worked as one system. Now, structure number 2. Structure number 2, we try to keep everything the same, but the only thing we changed is went from 3 core spacing down to 2 core spacing. So in our case, every 16 inches center on center for the grid. Notice not much change when you talk about that 0.4 G, still under 3 millimeters and under 10 millimeters for settlement and displacement. Look at your second shaking though. 10 millimeters to 30 millimeters for settlement, displacement was under 50. Now remember, the 3 core spacing was 30 to 90 millimeters of settlement. So we cut it by a third just by going from 3 block spacing down to 2 block spacing. So to us, this was one of the first eye openers, other than the fact that we didn't have catastrophic failure, right? All of a sudden we're like, wow, that made a huge difference. So structure number 3, what we did is we kind of went to what we recommended at the time. So you'll see we went down to 60% grid lengths. So most of the grids were only 1.68 meters in length, but we did lengthen the top layer of geogrid. You'll also notice there's a little bit of shading right here in this top couple courses. Why? Because at the time, the loading of the seismic was much top heavier than what we see today. And so connection strength, soil pullout, we would grout that top layer of grid into the block. And so we would physically pour concrete so that grid couldn't pull out of that system. And that was the way we would do like a positive connection. And we thought that would be a requirement based on, the codes at the time, the methodology at the time. So you can see 0.6H, 0.9H for the grid lengths, 2 core spacing, same soil, same 37-degree soil. So we try to keep things as consistent. But notice, even though we went down to 60% grid lengths, our settlement and deformation didn't change much. which was great, right? Now all of a sudden we're like, okay, 70%, 73% grid length, we go down to 60% grid length, but just lengthen that top layer geogrid. And we liked that, to be honest, because now we had two failure mechanisms, or we branched or bridged over the major one, because what we saw was test after test after test that the grid held things together. So most of the major deformation happened right where the grid length stopped. By lengthening the top layer geogrid, we kind of softened that a little bit, and that was cool. All right, so structure number 4, we kept everything the same from structure number 3, except we used a poor soil. So instead of the sand, now this was still a manufactured sand, but it was a 26-degree soil as tested by shear strength. Not much change. Okay, we did get a little bit more displacement and settlement, but it was hard to determine which one was worse. But it was good to kind of have that, because that was our new baseline. Now, if we have clay soils or poor soils, what does that do? So as we're getting more comfortable with how the system's working, so let's stress this out a little bit. So structure number 5, what we did, and I hope this shows up on you. I couldn't get the white background to work here a little bit, but instead of 2 block spacing or 3 block spacing, we even had recommendations, again, back in 2002, people were still looking at these as almost tieback systems. And so they were doing 4 block spacing. And so we thought we'd test it, see what happens if we go to 60% grid lengths, but 4 block spacing. And major movement, major settlement. It was actually one of the ones where we got so much push against it that it was like, okay, this could be failure. But and I got to remember, guys, I keep forgetting, structure number 3 is when we introduced that vertical component. So some 3, 4, and 5, we went, when we had that horizontal of 0.4 G, we introduced that up and down movement of half that, because that's actually similar to what they saw in the Kobe earthquake. And when we went to 0.8 G, we had that vertical component of 0.4. And now structure number 6, this is where they said, okay, we're going to just break this thing. What do we need to do? So we went to 4 core spacing, poor soils, but then what we wanted to do is see what would happen if we cut our lips off. And if you're familiar with Allen block, it's got a front lip. That's our shear connection. That's the way we align the batters and get things to line up. And so we thought, okay, we couldn't get the blocks to displace. Maybe that front lip is acting too good, if that's possible. So we cut the lips off because we wanted to see what would happen if there was no interaction between the blocks itself. And you can see we got some movement. Obviously, the blocks displaced at this point. So structure number 6 really kind of hammered home the fact that you need some type of a shear connection. We didn't qualify it that it had to be a front lip. Yes, the researchers thought that front lip was pretty dynamic because it's right there at the face of the wall where that movement was. But somebody could get the rear lip or a pin or a clip or whatever it is. You need some type of a shear connection. So what we saw, and I want to just point this out to you guys, and I'm having a little problems with my mouse here all of a sudden. This to me is where this is that opening shot I had. But now if you look a little closer, look at some of these results. This to me is really what hammered the testing home. Look at this. Let me get a little closer. Look at how the grid area shows very little deformation. Yes, there's some surface cracking and stuff like that, but after or where that grid stops is where you see the major problem. Okay, so again, we had test after test after test that shows that grid holds that composite mass. And I got to admit, pretty relieved, because that was the assumption we're making in our design, right? We're assuming a composite mass that once we introduce the geogrid layers, the block, the rock, the soil, the grid, all is one system, and that is our weight to resist our forces. Well, we had a test that kind of proved it. And it kind of showed that. So great feather in the cap when it comes to how this systems work. Again, guys, if you have questions, please let me know as we go through this. One of the big things, all right, so we felt like we had a responsibility to test the system because we wanted to make sure people were comfortable using segment retaining walls, specifically Allen block, in high seismic zones. Well, this test did it. Our white papers, we did a series of presentations up and down in dynamic in high seismic zones. So it really helped change the thought process. And actually being flexible, it works in our favor. And then it did change the methodology. And this was interesting. Remember I told you about the grouted connection that we had at the top of the wall? We don't do that anymore. Why? Because we don't see the seismic loads the way they originally dreamt them up. You know, here we're looking at a free body diagram. We got the face of the wall right here. We know that soils act as like a triangle pressure distribution. So very little pressure on top. The deeper you go, the more pressure you feel. So the bulk of that soil pressure is at the base of the wall. What you're seeing here on the right-hand side mimics the dynamic load of a seismic event. Now that was not always the way. It's more of a uniform pressure. So it's the same type of pressure on the top as it is on the bottom. And that is a direct result of our testing that we did over in Japan. It shows that it was kind of a uniform pressure distribution behind the wall with all of the different pressure gauge that was instrumented on that wall. The old thought process was you had very little pressure at the bottom, but you had a maximum pressure at the top. So I wouldn't say a complete reverse of the active pressure, but it was a much higher pressure at the top of the wall. Kind of like that flagpole whipping effect is really what they kind of thought about in the original concept. Because of our testing, we've proved it over and over and over again that that dynamic load is more uniform. It changed the methodology, which was great. Now all of a sudden we've got something more accurate than what was originally thought of. So it's good. So a great way to kind of advance the industry. And then we also know that that distribution is the key. Because of that, it changes our mentality of that two core spacing. So I'm going to kind of switch gears here a little bit and talk a little bit more about best practices. But for us, best practices launched in our own mentality back in when this seismic testing was done in 2002, 2003. Okay, so with that, I've got another poll question for you. Let's see if I can get my mouse to work here real quick. If I go to this, I've got how do you determine the seismic coefficients for your design? And I'm going to go ahead and sorry, let's hide this and go back to this question and launch this one. So now you get a chance again to give me your answer. And I got to give you a couple options. Obviously, local codes. We've got in the states, United States here, we got the USGS website. And then we also have, maybe you don't do it. Maybe you leave it up to the geotechnical engineer. And so give me your answer here if you get a chance. Let me know what your thoughts are. And again, I only have a couple of you guys and wonder if you guys are reading each other's minds, because I got 100% option in. And if I go ahead and close this and share the results, you guys might be laughing at yourselves as well. But I do have 100% of you guys said that it's based on websites, all right? And really, it's all the above, to be honest. There's no right or wrong answer. I got to tell you, here in Block, we do a lot of preliminary designs. We consult with people around the world. We tend to lead, especially here in the States, we lean on that USGS website. All right, I'm going to get into that here a little bit, but that's just a recommendation, right? That's just based on their information. Local codes can always govern. You know, they can always be more stringent than even what's outlaid in the USGS. And by all means, the geotechnical engineer, part of their scope of work is probably to determine the constructability of a site. And so they're probably looking at the site-specific acceleration or dynamic environments. And they're looking at the USGS and they're looking at other things too. But you know, if you're working with a site civil or a site geotechnical engineer, they're going to give you some strong recommendations of what the seismic coefficient should look like. So all of that is a possibility. So go ahead, I'm going to hide this now and get back to that presentation. And I'm going to move forward with this. And so you're going to get a copy of this presentation, and this link is going to be right in the PDF as well. But this is the link to the USGS site. And it's nothing more than you bring in the latitude and longitude of your location, and it'll give you back your different values. And for us, we look at the AS value, or the seismic coefficient. Now, that's just a guideline, right? It's because local codes, a lot of times they're going to go ahead and talk about you can even half that value. And so AASHTO gives us some guidelines here in the States that, you know, I can take that here, the value is 0.203. Well, because retaining walls is kind of deemed as a non-critical structure where it's not a building or something like that, you can go ahead and take that value and cut it by half. That's completely up to the designing engineer and what they want to do and if that's acceptable in the code. loads. So just use that information as you go through this. Other thing that's in the best practices, yes, you need to understand the seismic design requirement, but look at the next couple recommendations that's in best practices. Closer grid spacing, 16-inch spacing, right? That's right out of our seismic testing. Extend the top layer geogrid. Boy, that sounds familiar too, right out of our seismic testing. And then we do like the idea of using selective structural backfill. Even though we didn't get a direct correlation in our testing, we know through personal experience that building in a better wall or better backfill is going to give you better results, especially then you don't have to worry about potential liquefaction of clay soils. If it gets a little wet and then a dynamic load, it could actually liquefy, and now you've got no strength in that soil, and it could actually bulge and fail that retaining wall. So best practices, I keep talking about that, and you guys probably are even aware of best practices because we put that in publication in 2015. All right, 2015 is when we released best practices. NCMA, I kept coming back to them, they released their version of the best practices in 2017. But like I said, we've been preaching this for the 18 years prior to this, because of our seismic testing. So great way to kind of summarize all this stuff. And we've got a full test report. And again, this will be part of the follow-up email to you guys. So you got our executive summary and what was learned and how this got to be a pretty good test, not only for Allen Block, but for our industry as well. So, but Allen Block is still the only retaining wall product that has done the full-scale seismic testing. We're pretty proud of that. So keep that in mind. All right, let's talk about slopes above these walls. Why? Because I often think there's a double standard going on in our industry. You know, here we keep talking about retaining walls and we keep talking about what the design requirements are, and you're looking at overturning and pull out of soil and everything that goes along with the retaining wall. But then you stack this massive slope above the wall that's never going to be stable in a dynamic event. And so when the earthquake hits, now the slope fails and the retaining wall is just going for a ride. And so to us, we've always kind of looked at these retaining walls as less as walls and more as reinforced slopes, because that's really what they are. They're just almost straight up and down because of that block providing that structural form to backfill and compact as you go through this. But to me and to us in our industry, anything you do for your retaining wall design must be applied to your slope above the wall or your slope stability. So if you're taking an acceleration coefficient of 0.2, like we saw in the USGS printout there, that same analysis or that same acceleration coefficient should be used in any slope stability analysis that you're doing. And so critical to do that. So that way, you know, you've got an entire system that is functioning just fine. All right, I did have a question pop up. I appreciate that. I'm going to go ahead and read this since I haven't read it yet. It says, how is the soil dynamic load determined in order to determine the load on the retaining wall? Great question. I'm going to get into that here in just a little bit. But in essence, you've got your, if you're familiar with soil mechanics, right? You have your K sub A, because we use Coulomb's earth pressure coefficient. So we calculate our K sub A, and then we multiply that times your depth and unit weight of your soil, and you get that active pressure coefficient. Think of it the same way. I've got the height of the wall, but now what we do is we're going to calculate a dynamic K sub A. All right, so that's going to add additional force to this. So you always have your soil loads, going back to that free body diagram. You always have your static soil loads. What we're going to do is add a dynamic load. Now that K sub A value is going to be calculated using, and this is a perfect timing for that question, by the way, usually using Mononobe-Jacobi. All right, I call it MO for short. In other words, I keep talking about Mononobe-Jacobi and I might get twisted in my tongue, but MO is the methodology that is probably used the most when you're talking about dynamic. And it's just that a separate equation, you run through it and it takes in your acceleration coefficient. It does take in the deflection that you have, but you simply just run that calculation and you get a second K sub A value, a dynamic K sub A value. And now you can go ahead and multiply that times your height and whatever else, and you get that additional load behind that wall. So that's how it's calculated. Now, if you are familiar with the MO equation, there are limitations. It is not bulletproof. In fact, I'm kind of showing you one right here. MO falls apart as soon as you've got high steep slopes above this wall and maybe some poor soils. Those two combinations, the Mononobe-Okobe earthquake breaks apart. In fact, what happens is, because in the equation, numerators and denominators, the denominator starts approaching 0. And if you're familiar with math, you can't have a denominator approaching 0. It kind of blows everything up. So what we do here, you can see on the left-hand side, a 7-foot high wall with a 2-to-1 slope. And a 2-to-1 slope, if you look close, that would give you about a 26.6 degree backfill or back slope here. Without seismic, my grid lengths are pretty typical, 60% grid lengths, 90% on top. As soon as I add seismic, look at my back slope. It drops. I can't get to 26.6 because of that limitation. So what our software does, instead of just giving you a big fat no, it's going to run through the analysis and find out how steep that slope can be and actually get to those results. So it truncates the slope and gives you saying, okay, I can get to almost 20 degrees, 19.8, before that falls apart. So that's the key with Mononobe-Okobe. It's probably the most widely used, but there are some limitations. Now, with computers, the analysis for the trial wedge method is now possible. It can be done faster, and it actually models site conditions a little bit easier. There isn't that same limitation because I'm not doing the numerator denominator. It's all basically trial wedges. I take that wedge soil, I determine what that is, so I'm doing numerous hundreds and thousands of iterations to do this trial wedge. So I can do those steep slopes. I can do those analysis and not have it be a problem. So when I have that high seismic coefficient with that steep slope or poor soils, like the low friction angle, that soil, trial wedge can be used. Now, keep in mind, trial wedge isn't bulletproof either. I mean, if I'm trying to do a massive wall or a massive slope above that wall, I got to use some engineering judgment here a little bit and double check. And so let's get into how this affects, how this brings in. And AB Walls is with the tool that we use almost exclusively here at Allen Block. And it's not a global stability program. I can export it to global, like a RISA Plus program, but it does do the seismic, the slope stability above the wall. And so when you do your calculations, you can do a full wall profile, cut it into multiple cross sections. So if you're familiar with the AB walls, that hasn't changed. Now, when you get into your section design, to get into the dynamic load, you just go to the soil parameters or the design parameters, which is in the lower left-hand corner of your screen. And what that does is that just activates a tab for you. And it's the same tab that your soil information's on. So when you first open up the program and you're working through it, it's going to default to the soil tab right away. And you can bring in your friction angles, your site soils, but you can, instead of waiting for it, you can toggle over to the seismic parameters and enter in your acceleration coefficient. All right, so that's that peak ground acceleration coefficient that you're grabbing from your codes or the websites. But remember I said the MO allows for deflection. And because segmental retaining walls are flexible, the code allows us a maximum of 3 inches. And that allows you to reduce that dynamic load. Think about it. If I've got a rigid structure and it can't move, all 100% of that dynamic load gets transferred. If I can flex even just a little bit, it reduces that pressure. That is one of the reasons why we were very comfortable doing our seismic test 18 years ago, because we knew we had a system that would flex and move and work with the dynamic load and not just always resist it. But again, AB Walls is just a design tool. You can go ahead and change that if you want. Now, I would never go more than 3 inches, but if you tighten that up, what that does is it's going to increase the pressure on your wall. But you can see we default to the industry standard of 3 inches. And then what happens is once you hit calculate, you always have your static conditions. We never ignore static. Okay, so in your static conditions, we still look at, your sliding and overturning. We still look at that grid overstress, pull out a block, pull out a soil, so that internal analysis. But you also have the internal or the seismic equations now, or the seismic safety factors, And so now you get a second set of overturning, sliding, bearing capacity, and internal of grid overstress, block pullout, soil pullout. But you'll notice the safety factor requirements are not as steep. So sliding and overturning, sliding is 1.5 for static, but it's only 1.125 in seismic. Why? Because seismic is a short-term load, so you can actually take 75% of your static conditions. So that's the default values of the safety factors. Great question here again. I did get another one. Is there a height limitation when using 3-inch maximum will deflection? No, that's very insightful. So that's a great question. There is no max height. That 3-inch of deflection is being used on a 3-foot high wall, or a 33-foot high wall, or a 53-foot high wall. So yeah, one would argue that if I can go 3 inches on a 3-foot high wall, can I get a little bit more? Well, at some point, if you get more than 3 inches of deflection, you're going to get some major movement and probably result in problems above that wall. So we always kind of use that 3-inch of deflection as kind of that control. So great question. I appreciate that. Very insightful on that one. So again, safety factors for seismic, 75% of your static conditions, and then you're just comparing it. Everything's right in front of you. You can use your judgment, but you can see the software for us. We always default to 60% grid lengths, and we'll lengthen that top layer of geogrid right away. Now, if you go through your calculations and you try to do a steep slope, let's say you have that 2-to-1 slope above the wall and you've got soils that are more of a clay type material, the first time you pop up, it's going to say, listen, you're exceeding the capacity of that slope above the wall with Mononobe. So as the designing engineer, you can decide to use the MO method, or you can do the trial wedge. But if you use the MO, what are you going to see? It's going to truncate that slope to whatever allows it to get the analysis calculated. If you use trial wedge, you're going to get that full slope and full result. Now, I mentioned it's not bulletproof. Let me give you some results here, and you're going to find this eye-opening. At least I do whenever I run these analysis. So look in the left-hand side. This would be for no slope. These are all seismic designs. No slope above that wall, very simple, 60%, 90% on top, no problems with safety factors. If I do a 2-to-1 slope in MO, it'll truncate it to that 19.8 like we showed before, and we get the 10 and 13. That is still well above 60%. I mean, we're talking about an 8-foot high wall here, 7 feet exposed, so we got a little bit of buried block. So we're well over 100% grid lengths, and that's just the MO. Look at trial wedge. Okay, still same height here, but I would need 30.5 foot of grid to reduce or to satisfy that earth pressure that's being not only from the soil, but also that massive dynamic load. Think about how much weight that is and how much pressure that's putting on that wall. And this, to me, is the secret behind segment retaining walls and seismic design. I'm not throwing anybody under the bus, but what is very often done, even by engineers, but specifically developers and customers, is they like to limit the height of a wall because they think that's the expensive part. They think the block and the grid, it's not the block and the grid, it's all the excavation, it's all the moving of dirt, it's that installation side. The block and the grid is peanuts compared to the big picture, but they like to limit the height because they think they're going to get a cheaper system. But then unfortunately, they still got a grade they got to match. So they try to put this steep slope above the wall, and then they got seismic event, and then they wonder why it's economically not feasible. They could just change it ever so slightly. They can go ahead and raise the wall height. That would reduce that slope. And if you reduce that slope, you just dramatically changed that dynamic load. Slopes and seismic, they are not friends of each other. Right? And so if you can reduce that slope, now all of a sudden, you're not getting 30.5 foot of grid. You're probably going to get back something closer to that 60, 70% grid lengths again. So you're going to get something closer to the level conditions. So I always tell engineers, don't be afraid to raise the wall height. Right? If you raise the wall height, you reduce your slope, and you're probably going to have a better solution when it's all said and done. Plus, you don't have to worry about the global or the instability of that slope when you have the dynamic event. All right, so that's the key. What STC was the analysis based on when the wall in the wall comparison. So this was at 0.4. This would have been the example that we had way back when. So in the first part of this presentation. So yeah, so we used just 0.4 G as kind of the control on this one. Soils were just our default value at 30 degrees. So kind of giving you a little background on that. So probably should put that on the screen here a little bit so you can kind of get that. But yeah, we're not, these are just screenshots from our software kind of in support of the talking point. So great question here. Any other questions? Because really, I'm at the point now where I'm just kind of reviewing here for you a little bit. You know, we know these walls function great in a dynamic environment. In fact, to me, and I realize I say it, I got Allen block on my polo here, right? But I know segmental retaining walls are some of your best solutions when you are in a dynamic environment. So I am very comfortable recommending our use. Let's be smart about it. Let's raise the height. Let's make sure we reduce the slopes above these walls. If we can do that, now we've got a better solution, as I mentioned before. But you know, this full-scale seismic testing led the way for our industry, and that's 18 years old already. But it's still, what we learned is still being applied, that uniform pressure distribution behind, right? That it changed that seismic load. And I know I sound very passionate about it, but that was a game changer for our industry. No longer was it being top loaded like that flagpole effect that we were talking about. It is now more uniform, because that is what we saw over and over and over again in our seismic results. And then the last thing is slopes above the wall. And I know I sound like a broken record on this, but slopes and seismic are not, they're not friends of each other. And so trying to balance those two can often lead to an engineer's headache, trying to figure out how you do a retaining wall design with a steep slope. Simplify it. Just reduce that slope by raising the grade. You might get some funny looks from counterparts, and especially your customer, but it is really sometimes your best and economical solution when you're talking about that. So great way. Let's see. I got one guy that is asking some great questions. And so how is a surcharge load converted to a seismic load on a retaining wall? It's a little different. So when you think about, there's two thought processes on this. I want to give you one. I'm going to answer your question the way I think you're asking it. As soon as you have like that parking lot or driveway or something above, you just add that surcharge load to it. So think about that free body diagram we had before, right? We have the active soil load, so that's that triangle pressure distribution. Then you would have your surcharge load, which is a uniform load, and then I would even have another dynamic load on top of that. And so you would just take that case of A, that new case of A value from a Montanobi, you just multiply time your surcharge load, and you get that change in dynamic load. Now, where I could think you're interpreting this question, or one way I want to give you a talking point, one of the old methods that we used to do when we didn't have the trial wedge is we would convert slopes into surcharges. We would take the load of the soil above, and we would model that as a dead load above. You can kind of see that's kind of shortchanging the analysis a little bit. You're not getting a true dynamic load. So we don't really recommend converting slopes to surcharges anymore. Now, when you have a surcharge, we just simply apply the same Montanovian equations that we normally do, and we get your active surcharge, your active pressure, your surcharge pressure, and your dynamic load, and it all gets added, and it's got to be resisted by your lateral pressure. So great question. Hopefully I answered it that way, but some very insightful questions as we've gone through this. Again, continue asking them as we go through, but at this time, if you don't have any other questions, what I want to do is kind of recap a few things for you. First, thank you for your participation. Second, you're going to get an email from us here tomorrow morning. It's going to have all the attachments I was talking about before. It's going to have the evaluation for you. So if you want continuing education credits, we had a little problem getting things attached. In fact, GoToWebinar was not allowing us to attach it to the session here for some reason. So we're going to follow up with an email with that evaluation. Please complete that evaluation, send it back to us. We'll get you your continuing education credits for attending this session. But please let us know how it can be a resource. right? We get to do retaining walls every day, and fun and exciting as that sounds, that's what we get to do. And we know you guys get pulled in a lot of different directions. So if we can help simplify your life, answer a question, bounce ideas off of each other, we're happy to do that. And we're honored if you use Allen Block as that potential solution for your grade change. We've got a production partner network that we feel is second to none, with boots on the ground and guys that can provide some real world experience to contractors and stuff out there. But let us know how we can be a resource. But I haven't had any other questions pop in. So I guess with that, I'm finished a little bit early, but still going to count for your training. And I appreciate your time and the compliment that just came through. And we'll look forward to working with you guys again here in the near future. Thanks again for your time. Be safe out there, and we'll see you again real soon.